it is important to solve the differential equation. In the upcoming videos, I will discuss about the solution of first order, first degree differential equation. In this video, I will discuss about the geometrical interpretation and form of a first order and first degree differential equation. This one here is the general form of a first order, first degree differential equation. Now, this can be modified to write like this second form here. So from how can we separate these dy and dx terms as they are a single term? This is the derivative of the function y. To separate them, we use the concept of differential and approximation. So what we want to find out here, how can we write dy equals to f dash x dx? Okay, so suppose we have a function y equals to fx and the derivative is defined as f dash x equals to limit delta x tends to 0 delta y by delta x. So delta y is the increment in y direction and delta x is the increment in the x direction. Let us put it graphically. So suppose we have a function like this and suppose this length is delta x. So and this length here is delta y. So if we want to find out the derivative, this is it. So for the original curve, the increment can be written as delta y and delta x, but for the tangent it can be written as dx, and same, that increment in the direction of the tangent is dy. So these dx and dy, they are the approximations or they are the differentials. This is the differential of x and this is the differential of y. So what we can do, we can always write delta x equals to dx, and for very small delta x or dx, we can write delta y equals to dy. And also this delta y by delta x can be written as f dash x, and therefore delta y equals to f dash x delta x, and which in turn can be written as dy equals to f dash x dx. So here we are not separating the derivative, rather we are using the differential of x and differential of y. Okay. So suppose we have a function like this. So in this case, we can always separate this. We can write it as dy equals to this dy dx. This is the derivative, and these two here, they are the differential of x and y. So we can write it like this, and by substituting this as psi xy divided by phi xy, we can put this equation in this form. Okay. Okay, next is the geometrical interpretation of a first order, first degree differential equation. So here I have written this form, although this form is not quite right, as here it is a function of dy dx. Therefore, it may have the power 2 of dy dx. However, here we are speaking about the first degree differential equation. So the general form must be in this form, this. So this equation establishes a relation between the coordinates of a curve and its tangent. Suppose we have a curve like this y function. This is known as integral curve, which is the solution of this differential equation. So this is the solution curve. At each point of the solution curve xy, we can draw a tangent. So the slope of this tangent, which is the dy dx part, is related to the coordinate of that point by this function. So this is the relation between the slope of a tangent at some particular point and between the coordinate of that particular point. This relation is known as differential equation, and the solution of this differential equation gives one parameter and one parameter family of curves, as this is the first order differential equation. So let us understand by an example. So here we have this example, dy dx equals to minus xy. So obviously by using the differential, we can write as minus x by y dx. Therefore, we can write like this, y into dy equals to minus x into dx, and by putting y dy plus x dx equals to 0. Next, we can integrate this equation. We will obtain y square by 2 plus x square by 2 equals to c. So it can be written in this form, x square plus y square equals to s square. So this is one parameter family of curve, and this is obviously the equation of circle which has the center at 0, 0 and varying radius. So we can plot it like this. So the family of concentric circles. What this differential equation is telling is that at each point of these curves, if we draw the tangent, the slope of the tangent will have this relationship with the coordinate of that point. Okay, so in the upcoming lectures, I will talk about how to solve a first order, first degree differential equation. We will start with the separation of variable method. Thank you for watching.